Hello, everyone. How are you doing? Hope you're enjoying the event till now. My name is Julian. I'm an applied cryptographer and computer scientist. And here at the front row with me is Carlo. He's a mathematician, PhD, and computer scientist. No, not computer scientist, but applied cryptographer too. We work at ERYX, where we do zero knowledge, recently blockchain, computer vision, LLMs, and purpose-built software development. And today we wanted to share some knowledge we gathered by doing something cool. That's the whole goal of the talk, like sharing something we did with you. So yeah, thanks to ZK Summit and ZK Podcast for giving us the space. And let's go. We'll be going over some GPU optimization basics, so bear with me. This talk won't be too technical in terms of GPU, but I'll get into some math, which shouldn't be hard in the context of zero knowledge, at least. So GPUs can be used for many things, right? Their original purpose was image and signal processing. That's the G in GPU graphic. But people have since harnessed their power for algebraic operations and data-intensive computations in general. So they bring some problems. When one wants to use the GPU for its power, one finds out that GPUs and CPUs have different memory spaces. So one cannot access the other's memory. And copying data from one memory space to the other is expensive, it's costly. More in the developer quality of life side, the presence of different memory types, it makes stuff difficult. It kind of makes it complex. So managing memory access is not easy. And there's also the fact that they're not ZK-oriented components. So as a developer, especially trying to build ZK over GPUs, one finds out that there are no primitives, there are no API facilitations for ZK in general. So that's the problems that GPU brings. But there's also benefits, of course. We wouldn't be having this talk if there weren't. When we launch threads to process our data, GPUs parallelize this very well. So even if they don't run at the literal same time, they do run in parallel, or concurrently, I mean. So the GPU is very good at making this code you're running run as fast as possible by parallelizing stuff and handling its own resources to help them use the resources of the GPU when they're available. And apart from that, there are increasingly available components. So every laptop has a GPU nowadays, and even if it's not specifically the best GPU there is, or the latest NVIDIA 5090, whatever, you can get your optimizations running on commodity hardware pretty well. We have run some of these benchmarks in laptops, and the results were very good, similar even. So yeah, there's also the fact that MacBooks, for example, that are closed hardware have the added benefit of us as developers being able to benchmark our programs in a more consistent way. So everyone that has a specific MacBook chip will have the same GPU, maybe with varying VRAM or something like that, but the parameters are controlled. So you know that maybe, I don't know, whatever generation of MacBook has these 3 options for VRAM, for instance. That's an added benefit of closed hardware solutions. And in this talk, we may focus a little bit on CUDA specifically. CUDA is NVIDIA's API. You might have heard of it. And there are a lot of architecture specifics about CUDA that help us optimize our code even further, apart from the implementation in GPU. For example, blocks and warps, memory banks, global memory, etc. This list is just for you to look at and see that there are possibilities. Don't bother remembering this. I mean, it's not important. It's just for you to know that there exists. There exists an alternative for even more optimization. So since I will be going into some examples of optimization, I'll first go into some preliminaries for you to understand these examples or to have context on them. First is Stu. Stu, some of you may know, is a prover, a ZK prover, based on Circle Starks and made by Starkware, right? And our challenge last year was to build a GPU implementation of Stu. So Stu boasted at the time to be the fastest prover there was in terms of hashes per second. And now when we built Stu GPU for Nethermind, we faced the challenge of first understanding the protocol. That was a big part of it. And since there was no GPU implementation yet, whatever we were making was like the first iteration of like Stu GPU. So that in itself brought value. And since it was the first iteration, you know, the phrase make it work, make it right, make it fast. Of course, we didn't make it fast at first. And we just focused on making it work. And by making it work, it was very fast. I mean, we didn't try optimizing it, and it still was very fast. You'll see right now. So yeah, no optimizations were planned, which means that some of you may even think of better optimizations for some stuff we're going to show today. In any case, did it work? I mean, was it faster? Well, I already spoiled that. Like, it was faster. And this is how much faster it was. This graph, in order to help you read it, goes like this. So at the very bottom, the x-axis has some of the steps that Stu takes in order to prove a trace, right? The execution of a trace. So for each step in the y-axis, we have the accumulated time taken to reach that step. So in total, a proof using CPU and ERYX, which is the orange line, takes about 2.5 seconds, right? Our GPU implementation takes way less than that, maybe in the order of 100 to 200 milliseconds for the same proof, which is about 20 times faster. And that's just implementing Stu in GPU, no optimizations, no nitpicking. That's just how fast it is. Just for completeness, this is not over a specific trace. In particular, we made this over a simulated trace that's named the wide Fibonacci, which is made to be big and wide for us to test the prover with as much data as possible, right? This talk will be focusing on examples in these parts, which are first a Merkle commitment, and then some stuff having to do with Fry. We won't go into detail, again, on Stu's protocol and stuff, but just so you know, this is where today's talk will focus on. Now, the first case study, batch inverse. Okay, so these are the parts that this first case study focuses on, right? We'll first review the, oh, did it skip a slide? No, okay, perfect. We'll first review the sequential algorithm that, batch inverse is as it is implemented in Stu. Then we'll parallelize it as it is implemented in Stu GPU. And then we'll compare them both to see how they fare against each other. So batch inverse is an algorithm with the objective of inverting a bunch of field elements. That's all. So you have a very big list of field elements, and you want their multiplicative inverse. Easy as that. Now, for the sequential algorithm, the one that's implemented in regular Stu using CPU, what they did was, since field inversion is a very complicated operation and computationally heavy, what we did was apply something called Montgomery's trick. Montgomery's trick allows us to circumvent somehow this expensive operation that is the field inversion, usually done with the extended Euclidean algorithm. For an example of Montgomery's trick, we'll take these 4 field elements, A1 through to A4, and we'll start inverting them by computing these little products that I'll show here. First one being beta 1, then beta 2 being the accumulated product from A1 through to A2, then beta 3 being the accumulated product from A1 through to A3, and so on and so forth. I'll refer to these as either accumulated or partial products, so you know what they are. And just for completion, there's a more efficient way of doing this, which is using the previous accumulated product to save some multiplications. But at the end of the day, calculating beta 4 takes the same time here and here. But you save some computations. So after we have our accumulated products, we want to invert, we want to use the extended Euclidean algorithm as little as possible. So we use it only once here to invert the final accumulated product, beta sub 4. And yeah, that's the only point here in which we will use this inversion. Then with our already computed inversion, which is this one, we use another partial product, which is beta sub 3, to cancel out the terms that don't matter to us in order to obtain the inversion of a sub 4. So intuitively, what we're doing here is this, right? The first fraction, like the fraction, the 1 over a1 through to a4, is beta 4 to the minus 1. This is the inversion of beta sub 4. Easy as that. And then beta sub 3 is used to cancel out the terms. So you cancel out a1 through to a3, and they're left with a4 in the denominator. So it's inverted. Now we compute the same way we compute beta sub 3 inverted by doing something very similar. We use beta sub 4 inverted once again, but this time we only cancel out the a4 term this way. So beta sub 4 inverted is this whole thing, as I said before, and then we cancel out the a4 term in order to get this. This is beta sub 3 inverted, like intuitively, right? So now we know how to calculate the inversion of one of the elements, the final one, and one of the partial products. Each of these calculations only took one multiplication, one field multiplication. With the same idea, we can compute the inversion of a sub 3 using the previous results, right? Beta sub 3 inverted is used here. We calculate it here, and we use it below. Then there's also the fact that we calculate the next beta, like the next accumulated product for calculating the next inversion. Once again, beta sub 2 inverted is used to calculate a sub 2 inverted. And the idea is the same up until we reach our final element, which is a sub 1 inverted, which, as you remember, is equal to the first accumulated product. So you just invert that, and you have your result. I hope everything's clear till now. But if anyone has any questions, please save them up for later. I'll make sure to go in depth with whatever math you missed. But in any case, I think this is easier than most ZK math. So yeah. What we did is, for an array of size n, we replaced n field inversions with 3 n field multiplications and only 1 field inversion. I don't have the data of how many multiplications are needed for the field inversion, but I can tell you this is a fair trade. Like we like this. This is perfect. So we need n multiplications to build the accumulated products or the partial products. Then we need to invert the final one, and then we need 2 multiplications to compute each element we want to invert. Now, you may have observed, as I told you when we were explaining the equations, that this cannot be parallelized as is, because I had to show you that the accumulated products, when inverted, were calculated sequentially, right? So, for instance, calculating the accumulated products requires the previous ones, and when we were deconstructing the inversions, that also required the previous values. So there's a strictly inherently sequential thing going on with the way the trick is built or implemented here. So we'll adapt it a little bit for it to be parallelized, which is what one would do when one wants to parallelize the algorithms for GPU. We take the same elements we want to invert, but now we'll make an assumption. We'll assume the amount of elements to invert is a power of 2. Just for completion, for ease of building a tree-like structure, which we'll build in the next slide. But let's say you want to invert 3 elements or something that's not a power of 2. then you just fill the list with whatever number you want to invert as a discarding number, like 1 or whatever. So there's no loss of generality here. And yeah, let's suppose the amount is power of 2. And as I said, we build a tree-like structure. First, we calculate this new kind of partial product, which is beta sub 1 through 2. It's understandable, right? It only takes A1 and A2. In the other side of the tree, we compute beta sub 3 through 4, which is A3 times A4. And now I'll show you the root, which reveals the true purpose of the notation, which is the way, or rather, the index at which the multiplication starts, or the product starts, comma, the index at which it ends. So beta sub 1 through 4 means we're multiplying all the numbers between 1 and 4. In any case, even if the notation is not clear, I think this is easy to understand. You only take partial products in a tree-like structure, binary tree-like structure. And now, you may notice that in the same level of the tree, each multiplication is independent. So we can parallelize the same level of the tree, right? Beta sub 1, 2 does not depend on anything calculated by beta sub 3, 4. This allows us to parallelize this accumulated product calculation. Now, when we have the roots of the tree, we invert it the same way as before, the whole accumulated product. And now, we want to deconstruct this tree, the same way as we did before. But now it's more graphically understandable. So we use the inversion of beta 1 through 4 to compute the inversion of the left side, of the left accumulated product, which is beta 1 through 2, by canceling out the terms that we don't want, which are in beta sub 3, 4. This is how it's done intuitively, the same way as before. Beta sub 1 through 4 inverted is always the whole product, and then we only cancel out A3 and A4. Easy as before. You get 1 over A1 and A2, which is beta sub 1 through 2 inverted. Easy as that. We can do the same thing on the other side of the tree, right? And get beta sub 3, 4. And then once we have the partial products, we can get the leaves of the tree, which are the result of this algorithm, actually. A sub 1 inverted uses this partial multiplication inversion and cancels out the term that it doesn't need. Then A sub 2 inverted does the same, and so on and so forth. I think it's clear. Once again, if anyone has any questions, please let me know later. The point is that, once again, since we built this in a tree-like structure, we can parallelize each level, which allows for the use or the harnessing of GPU power. And even after this parallelization we did, we could apply further specific optimizations, like I said before, like the use of shared memory, or, for example, consecutive memory accessing. Consecutive memory accessing takes advantage of the fact that your data is consecutively stored in memory and uses operations that apply that are applied to these consecutive datums at the same time, for instance. All of this helps us speed up our implementation even further. Now, this is a performance difference. This is the amount of time taken for each algorithm. And, well, you see it's a very big difference. We did some heavy math here, or we had to do some work. Even if it's not difficult, we had to do some work for the trick. Oh yeah, please. I was going to mention that. That's a good question. I mean, it's the CPU ERYX implementation is the one I showed before, which was the sequential one, but it also harnesses ERYX power. A single instruction, multiple data. There's also an ERYX talk after this one. It's great. I mean, Carlo here was participating in that implementation, but at least with today's hardware, I mean, GPU heavily outperforms CPU even when using ERYX. The only thing we varied is this way of building the products, which is using the Merkle tree. But I'll give you a slightly different example, which does not have any math mumbo jumbo or any complicated tricks like Montgomery's. In any case, it's a 75 times improvement for a list of 2 to the power of 24 elements. Now this is how it scales. So the difference I showed you here, or in the previous slide, is this point. And we can see that it improves between 66 times and 79 times with the use of GPU. Maybe it's not clear why, to some of you, why the graph grows so big, but it only grows from 66 to 79. And that's because the blue line, which is the GPU performance, also grows a little bit. Only that it's barely perceivable, I mean. So the next case study, oh, sorry, you wanted to take a picture. In any case, you can probably perceive it. The next case study, Merkle trees. This is done in this step of the proof generation of Stu, which wants to, yeah. Oh, yeah. This one?
So does it mean where the dot is commit Merkle tree? Is it where the procedure starts or where it ends?
Sorry, I don't understand the question.
It's cumulative, right? So,
yeah, this is cumulative, yeah.
So ending up between 500 and 1,000 accumulated time taken, is it after Merkle tree or at commitment or before?
Oh, you mean if this graph is accumulated or not?
No,
or you mean this one?
So it happens between the second dot and the third.
Yeah, yeah.
So really the constraint point-wise eval is much more expensive?
Well, I mean, it's hard to see the difference in the GPU line because it's so thin, like...
No, just on CPU, I'm surprised that...
Oh, yeah. I mean...
I would have expected that the huge increase is
well,
actually the Merkle commit.
We weren't the ones that implemented that, but I think that's a good thing to look into later. We can talk about that if you're interested after the talk. In any case, the algorithm builds a Merkle tree to commit a bunch of polynomial evaluations. So it's not just one Merkle tree, right? I mean, it is just one Merkle tree. You want the root as a commitment, but it is a lot of polynomial evaluations. And we want to commit this for the purpose of the protocol, right? Stu. But for this implementation, we won't look into the math tricks. We'll only look over some numbers, because once again, there are no math tricks. Now, as a side note, we use Blake 2S for hashing in this example, which was also implemented in GPU, but it works with any other hash function. Without any mathematical workarounds, once again, we achieved an incredible increment or increase in performance. The way we parallelize this is the same way we parallelize the tree-based Montgomery trick. If we want to parallelize the way we build a tree, we usually parallelize each layer of the tree. Since a layer of the tree depends on the one below it, then we cannot separate those inherently sequential steps, because you need one layer to compute the other, which you need to compute the next one. That's inherently sequential. So what we do here is we parallelize the building of each layer by themselves. The way we do that is just separating the layer into segments, or the level into segments, calculating each level in parallel, each segment in parallel, and then joining the results to build the next level. Simple as that. We're just separating a list into segments, computing each segment separately. That's it, no tricks. This is a performance increase. So CPU and AVX, as time scales, of course, takes more and more. GPU is way faster. Here, compared to CPU, it almost seems constant. And once again, this is CPU using AVX. It's not like strictly sequential. It's parallelizing using AVX instructions. So that takes a lot of work too. And AVX instructions are great, by the way. It goes from 11 times as fast to being 670 times as fast when the data size or the number of valuations goes to 2 to the power of 20. So there's a big difference, right? In any case, as a summary of what I wanted to show you today, what have we learned? Well, first of all, GPU parallelization is very powerful to make our ZK algorithms faster. A simple heuristic, like the one I showed you before, separating a list into segments, it goes a long way into making this way faster. For both high performance and commodity hardware GPUs. We tried this in like a 4090, in like a 1080, using laptops, using a tower PC. Every time, it's way faster. And also, as a side note, I mean, having a mixed team of mathematicians and computer scientists was great for this, since 2 is not an easy protocol to understand or even optimize. So yeah, this added a layer of understanding and collaboration that we didn't take into account, and it was great to have that. Thank you so very much. Once again, thanks to ZK Summit, and thank all of you for being here. Thanks for hearing me. Does anyone have any questions?
Was your CPU baseline code multi-threaded or just AVX?
I don't know. That's a good question. You think it was threaded? Yeah. No? Okay. Well, we don't know. I honestly don't know. Okay. I think it was not. I don't remember seeing any of that. Once again, we were in the team that built the CPU code that was like already done. And I don't remember seeing threading. But that's a good question, by the way. Yeah. Okay. Anyone else?
Brilliant. Well, thank you very much.
Thank you.
Obviously, the speakers are around all day if you want to grab them for any more questions. But we will end this talk here. So, thank you, Julian.